Good morning to everyone. Welcome you all to the webinar session. The session will start with an welcome address by Ms. N. Meenakshi, Assistant Professor ECE, and then the chief guest introduction will be given by Mr. M. A. Seshaya, Assistant Professor ECE, and then the webinar will be hand over to the chief guest, Mr. V.Hari Santhosh, Solution Architect, Honeywell, Germany, and then continued with an Q&A session, and then vote of thanks that will be given by Ms. M. Manjula, Assistant Professor EC. Thank you very much. Now I will hand over the session to Ms. N. Meenakshi, Assistant Professor EC, for the welcome address. Thank you.
Good morning to everyone. With the blessings of God Almighty and the constant support and guidance given by our correspondent ma'am, Dr. K.S. Lakshmi, and our secretary ma'am, Dr. K.S. Babai, and the motivating force of our college, our principal, Dr. P.K. Suresh, and our Dean Academics, Dr. K. Umarani. Today, the Department of ECE is conducting the fourth session of webinar series. It's my pleasure to welcome you all for this event. I welcome our speaker, Mr. V.Hari Santhosh, Solution Architect, Honeywell, Germany. It's very proud to inform you that he is an alumni of this department as well as institution. And I welcome you all for the session. Now, Mr. Seshaya will give introduction about our speaker. Thank you.
Good morning to everyone. I am very happy and proud to introduce our distinguished alumni, Mr. V.Hari Santhosh, the Solution Architect, Honeywell, Germany, as the speaker of this webinar. He has completed the Bachelor of Engineering in Electronics and Communication at Meenakshi Sundararajan Engineering College and Master degree at University of Applied Science, Hamburg, Germany. He has his area of specialization as Industry 4.0, Internet of Things, Cloud Technologies, Artificial Intelligence, Machine Learning, and Business Analysis. He has the working experience as Java trainer at NIIT and analysis at Verizon Enterprises Solution. Now, our beloved speaker will take over the session. Thank you.
Hello, everybody. So thank you so much for joining the session. And this is a wonderful opportunity for us to connect and talk about a lot of things. So I'm going to kickstart the presentation. Hope my screen is visible for everybody. So there was a small technical error. The presentation which I overridden was being removed. So I'm just sharing my screen immediately so that we don't get lost in time. So once again, everybody, thank you so much for joining the webinar today. So myself, Hari Santhosh, I'm currently working as a solutions architect in Honeywell, Germany. So I've been an alumni of our ECE department in Meenakshi Sundararajan Engineering College. So it warms my heart to be again here and talk with you all once again. So today's topic of webinar is future of manufacturing. So what is Industry 4.0 platform is all about, how we are using industrial IoT. So being an ECE engineer, this gives us an immense opportunity to see how all the technologies which we use will be implemented directly in industry and how industry IoT is going to shape the future. Of course, we will always get into the impact of 5G and communication technologies and how that will also serve as a backbone for the future of manufacturing. So with that said, we will proceed to the main agenda. So the important concept of manufacturing is factories of future. So currently, I would like to give a description about what is the main research area which I'm currently working on. So we set the stage with that and we proceed further. So what is factories of future? So that's the most important concept which we have to understand. Any industries or in any segment wherever manufacturing is being involved, right? That involves a lot of processing of data and aggregating things and producing results. So we understand that communication technologies is going to be the very essential step for making all these things possible. So currently, I am involved in smart factory department in Honeywell. So what we are doing here is we are producing gas meters here. So gas meters will be installed in lot of residential buildings to monitor like how much residential gas units has been used. So we are involving a lot of production plants which has a lot of robots, collaborative robots, and autonomous workstations which work in parallel to produce these sort of output. So we are basically synchronizing and establishing communication between different manufacturing equipments and producing results. So this is the main agenda which I wanted to share before we set the stage. So just a second. I believe there is a small glitch. My screen has been frozen. So let me just share the screen again. All right, perfect. So I believe we are all able to see the screen. So I wanted to set the stage by describing about the factory of the future. So what is factory of future? So basically, imagine this particular thing. We are currently living in a dynamic world. So the customers' demands will be frequently changing on a regular basis. So customers today they have a whole different expectations. They wanted to have customized products. So imagine me sitting in a, if at all we are a company who are producing cars, we wanted to produce custom cars. For example, a customer ask us to produce a particular design or a particular interiors or maybe a different type of steering or maybe a different type of color. So our factory should be able to handle the dynamic needs and understands the requirements of the customer before moving to production. So this is the requirements for the factory of future. So it should be more human centered and it should be based on circular economy. Based on customers demand, we should be able to dynamically adapt. So when I describe about industry 4.0, obviously I will be putting a lot of emphasis on cyber physical systems. So what is cyber physical systems? So cyber physical systems is nothing but converting the analog world to digital world. So the digitization technologies which we use to somehow connect all the physical appliances and putting them to internet or intranet, that concept is called cyber physical system. So whatever the physical products which are there in the product floor, that will be digitized and it will be moved to the cloud or to the enterprise solutions, and then we process everything and we produce the results. This is the analogy for factory of future. So now I'm going to talk about few important things here. So data. So the next important thing for factory of future is we will be working on a lot of big data. So the primary specialization of my mine is AI and ML. So what I'm trying to do is I'm trying to put all the appliances in the production floor, that is the factory, and I try to connect them to internet and I connect and collect a lot of data and I process them and I produce insights from them. So this is the primary role of data scientist, but I'm applying them in the context of industry using IIoT technology. So that is the job of Industry 4.0 engineer. So Industry 4.0 engineer will be working on both electronics domain as well as a lot of informatics domain. So it's a combination on coming together of all these various intradisciplines. So this is how we produce a lot of results. So data is the most important valuable resource. So this is a wonderful quote from Professor Edwards Deming. So without data, you are just another person with an opinion. So somehow we have to be having a proper data to validate all our claims. So this particular data revolution, right, it started long ago. It's not a new phenomenon. For example, Walter Pitts at 1943 itself, he conceptualized the idea of neural network. So people, when they talk about AI and neural network, this has been something which has been there till ages. Ideally, the concept of neurons and the concept of transmitters, all these concepts were the foundation stones which were laid long back. And then we all know the famous Moore's law, 1965. So the size of transistor will double down for every 2 years. So it was an exponential growth, and now we are almost reaching the saturation stage of Moore's law. But ideally, all these things were sort of a visions somewhere more than like before 50 years. But all these dreams came into reality very soon, and we are right now ushering in these visions which these people laid down. So another important aspect is the computer. Basically, the idea of cloud storage solution, right? So the concept of cloud is this. So if you have a physical server or if you have a hard disk, you can rent it out and you can somehow share it to users. So this is the idea of cloud computing. So when we have the idea of cloud computing, this particular technology was brought into action in 1983 itself. So CompuServe was a small startup during that time. They basically rented out physical computers, so you can use your photos and you can upload it like Dropbox or Google Drive to their system. So this idea, which is currently being implemented by AWS, GCP, this was done long back even in 1983. So this is the whole spectrum of industrial IoT. So we all have seen this figure in Gartner and then in Boston and consultancy groups. So all these consultancy big companies who make a lot of study, right? They are basically claiming that we will have 25 billion IoT devices by the end of 2021, and then we will have like 40% of IoT devices will be used in manufacturing industry, that is in factories, maybe in car factories or maybe in different working factories and things like that. So ideally, the entire potential for industries has been leveraged here in Germany. Fortunately, Germany has been a big industrial hub. We have a lot of companies like car companies like BMW, Audi, Volkswagen, and then Porsche. And then we also have like a lot of small and medium industries who are also producing a lot of production funks. Big companies, big robotics companies like KUKA, UR, and then a lot of Japanese giants are also having their market here. So all these manufacturing companies are using IoT and trying to bring value to their customers. So with this ever-growing need for connection and storing data, right, we find out that in future we may have 127 devices per second connecting to internet from a small factory floor. And lot of small companies and medium scale companies, they are also now beginning to realize that IoT is going to help them, and then they begin to slowly integrate these solutions and bring value to their customers. So these are the growth of the industrial internet of things. So now we understand that we will be using IoT and we will install it in shop floor, and then we begin to collect data from them. So what sort of data we collect? It's not going to be some textual data. For example, in our case, where we use different production lines to produce smart gas meters, we sort of use this sort of analogy. For example, we may have a raw camera feed which collects data from the production floor, and then we will also have a database system which collects regular transactional data, inputs coming from sensors, and then inputs coming from different intermediary functions, intermediary brokers. All these data will be collected together. So it's almost like bringing together of different disparate storage and processing them together. So we call that as big data. For fortunately, when a study was done by Dresner Advisory Services, it showed that manufacturing, which is at the end, is the least adoption, that is where the least adoption has been done. So only 12% of industrial IoT and big data has been leveraged. So that means we have a lot of opportunity there. In other industries like telecom, insurance, advertising, currently people are using internet technologies and big data to the very best knowledge. So manufacturing is the place where we have to work, and the opportunities is high here. So this is where we have to focus. And another important analogy which we talk in terms of manufacturing is dark data. So people will always say big data and things like that, but in industrial analogy we use this term dark data more frequently. So what is dark data, right? So like this pictures depicts, so we are basically seeing a big iceberg here, but what we are seeing is nothing but the tip of the iceberg. A lot of value is hidden beside the sea. So a lot of values are hidden beneath the lake. So we can relate this to to this because in industries, whatever data we show in customized dashboards, right? People will give custom ERP solutions, CRM solutions, make fancy visualizations, but those data, they are not at all that much meaningful. The impact provided by those data is very, very minimal. So a lot of information have been failed to process. So these are the information system which we have, but we never tried to explore it. So it's still hidden. So as a data analyst or as a data scientist or as an IIoT engineer who wanted to optimize the process, it is our responsibility to unearth this dark data and slowly get more and more value from it. So 65% of dark data is hidden within machine sky. So, and then the important aspect is if we don't use it immediately, 60% of data will lose its value. So let me give an example here to highlight and drive home my point. So imagine that we are working for Tesla, the company which is producing electric cars. And let's say that we are manufacturing, like 50 cars per hour or something like that. I know it's a very fancy number, but let's go with it. So when we manufacture 50 cars per hour, right? So imagine we have a assembly line one. So that is one assembly line where we have a camera sensor installed for identifying defects. And then when we say that a small error has been done somehow, and then it was done at the very start, but the device didn't fail to act upon it, and then it goes to the next stage, and slowly it has been processed till the end of the stage, and then we find out about this error. So meaning that we can't then the time is lost here, right? So this particular thing has been acted 1 hour later. This has to be done 1 hour before. So we basically lost a lot of time in between. So this sort of thing should be avoided. So 60% of data must be acted immediately so that it doesn't lose its value. This is the whole idea and concept behind the terminology dark data. So basically, dark data should be used for these companies to minimize regulatory compliances and then to generate future insights. But we never use them to the full potential. When we use them, it will be very, very good. So we will describe about processes which will help unearth this particular pyramid, and then we find more value about these data. This is the goal for us. So how to unearth that particular pyramid? That is what I'm going to say. These are the 4 levels of smart factory evolution. This is a very important slide. So I would say that the first step will be to make data available. So the first stage is available data. So data will be residing in multiple different sources, like I mentioned. We will have a camera feed, and then we may have a security sensor. We may have data coming from a QR code reader. Multiple different sources will be coming. We may get audio data, video data, signal related data, so different waveform related data. All these data will be first collected by us and put it in a single data lake. So make the data available first. So that's going to be the first step, and then we have to make it somehow accessible. So who should be able to access it? Because data protection is a very big and sensitive topic here. Let's say that in Europe we have this famous terminology called GDPR. So GDPR has been enforced by the European Union government to sort of give a protection for user data and manufacturing data. So unauthorized person shouldn't be able to access them. So only authorized party should be able to access it. So you have to make the accessibility layer above the available data so that only the authorized entity can view and access the data. And then the active data. So once you make the data accessible, right, you have to somehow make predictive models which allows you to go from reactive problem solving to proactive problem solving. You have to somehow understand and relate what sort of things needs to be done to make the system work in advance about what needs to be implemented. This is building intelligence. So we will slowly get into that there. And once you have active data, you should not just say that, hey, this device is going to break down in 5 minutes. You should prevent that breakdown, right? So that is action oriented data. So you have to somehow close the entire loop and say, hey, so I used this particular data, I used my algorithm, and now I'm estimating that this device may break down in 5 minutes. Now I have to act and I have to prevent it from happening. So that is action oriented data. So the whole idea for us is to go from using the available data and make the prediction and finally say and save the day by making the action and sort of completing the entire loop. When we execute it fully, right, the sort of time taken between insights to action will become much thinner. We should not just give insights, but we should also act on it. This is one driving philosophy which I wanted to emphasize on this particular slide. So let's move ahead. So what is Industry 4.1 platform? So I have more dedicated slides on this, but just to quickly touch base, right? Generally, in lot of factories, you will see this terminology MES, Manufacturing Executive Systems. So what does MES do? So manufacturing execution systems are nothing but more of a real-time database. Generally, in factory floors, we will have PLCs. PLCs is nothing but programmable logic controllers. This is something which is very, very inherent to us as electrical and electronic engineers. So using PLCs, we will send production related data immediately using Siemens or some other PLC controllers. We send it to MES system. So MES system will track what is being produced in the production floor on a real time basis. Let's say that we are producing a shoe. So if we are producing a shoe, if that shoe, one particular unit is traveling along the particular production line, it will say that, okay, it is in X point at this particular point in time. Now it is slowly moving to Y point. We will have different sensors placed along the assembly line to find out where that particular product has been going. So all the tracking functionalities will be logged in MES system. But this MES system, it's sort of an old school system. This system hasn't been evolved since ages. Now that we have IIoT in hand, we wanted to upgrade it and somehow build a lot of value to it. So how we update the MES system, that architectures will be something which I will be covering in the upcoming slides. Right. Let's go ahead now. This is the manufacturing execution platform, guys. So like I mentioned, this is how we are going to leverage, and this is how we are going to change how we make and how we sort of convert the old factory and make a move to smart factory. So at the end of the day, we are going to make a jump from old to smart factory. How we are going to do, I say that we have 5 stages for that. So first thing is edge processing. So edge processing is where we will all work. So we as an embedded engineers, and then we as communication engineers, our most emphasis will be given in phase 1. So I will just say this, without us, right, none of the other 4 steps is possible. So we will be the first and most important players here, because we are going to work on edge processing. Okay, so us as embedded and communication engineers, we will be the first people to give the segue to all other further services. So edge processing is the first stage, and then we have the 4 other stages: ingestion, data brokering, data processing, and making outputs. All these steps will be covered by us. So first, let's get into edge processing. So what is edge processing? So edge processing it's a very famous terminology which has been used in industries. So it's basically edge computing. So we use the microprocessors and advanced microcontrollers, and we directly process lot of big data applications in our factory itself. So it doesn't go to some Google server or some Amazon server storing, which is being used in some other countries. It's not sitting in America or in Europe. So we directly process it in our factory itself. So when we have data sensitive elements, right, people will prefer to use and process all these technologies in their factory itself. So we use maybe Jetson Nano, or we use Raspberry Pi, or any other advanced microprocessor to parallelly process all these things in the edge itself. So edge processing is going to be the key for us for factories, because companies have lot of sensitive information, my friends. So they have to somehow process all these things in a secure and robust way. So edge processing needs to be done so that it also saves the response time, and it also saves bandwidth and improves security. So once you process a lot of information directly on your factory, you will get millisecond latency. There would never be a dip, or there never be any loss of data. So how we achieve the edge processing? So basically the idea is to reduce the latency, then reduce the cost and improve the security. So these are the main IoT security concerns. The areas which I have highlighted at the right hand side, these are all the active areas which universities and researchers are working. Maybe when you enter into this arena and when we wanted to explore on these, if we focus on the verticals which are mentioned at the right side, you will be somewhere working along these areas. First is updating firmware and other software on devices. So embedded firmware updation. This is something which is very, very hot topic. People use OTA, over the air updates, and then they wanted to find ways to update the software in a more easy and transparent way. And then you have to somehow do some emulations as well. remember, lot and lot of edge devices has been in the market. There are many startups who are coming in this particular field. There are tech giants who are also producing softwares for different devices. So you have to somehow give the user the ability to use your edge device without purchasing it firsthand. So you shouldn't be telling them that first get my devices for $400 and then you can play around and do. You have to somehow make it accessible via cloud so people can test it out and install some software. And then once they play around with your IoT device, then they make a decision, purchasing decision, and then they do the ordering. This would be another important emphasis. So this will sort of elevate the options and make the users comfortable before buying our product. And then we should give them comprehensive training environments. This is again the same sort of setting which I already said. You should have a testing environment to test your IoT devices and see if it is going to be a good fit for your factory. And then security, use encryptions everywhere. So sort of make HTTPS communication as the default over the top communication so that nobody can eavesdrop your data going through your industry. And then you have to track and manage each IoT device. Somehow, if you do that, you will get a overall accessibility layer which sort of elevates and says that this particular production thing is in this particular point in time. And then you also manage it and make some real-time decisions on top of it. So these are all the areas. Again, the emphasis is more on security here because IIoT security is a $1 billion industry now. So it's almost worth to $20 billion US dollars now, because people wanted to target our smart home appliances and they wanted to hack it in some way, and somehow they wanted to bring down the entire thing. The same sort of thing, if it's happening in smart factory, that will result in multiplication of damage. So the damage done will be irreversible. So security, in security standpoint, lot of emphasis will be given when we select an edge device. And again, so this is something which is going to be a very important thing for us as embedded and communication engineers, because this is where we sort of connect any devices, guys, any devices which we wanted to connect and gather data. This is how we do. What we do, we will buy an edge controller. Let's say, for example, a Raspberry Pi or something, and then we will install a driver for it. For example, if I wanted to connect a semiconductor, or if I wanted to connect a Siemens PLC, or if I wanted to connect a KUKA robot, I will install the necessary drivers at my edge device. And then I say that I will write some customizations and ensure the data is collected in this particular protocol in this way. And then I send the data to my MES system. So factories MES system is the place where we do all the active real-time tracking and monitoring. Okay. So these are all the general protocols which we use. If we would be studying a lot of IoT protocols like MQTT, AMQP, but mostly in industries, especially in Germany, in Industry 4.0, we use this communication protocol called OPC-UA. So it is a very general protocol which we use, open protocol for communications. This particular thing, the biggest advantage of this particular OPC-UA standard protocol, it's been backed by IEEE. So this particular protocol will act as a data exchange mechanism from multiple vendors. So even if we have a different vendor like Siemens, or even if you buy something from Rexroth, both of them can communicate with each other using OPC-UA. So this is a standard which industry has set up to ensure multiple devices from multiple vendors can send information and everybody can talk in tandem with each other. So somehow we use this OPC-UA to get all the data and push it to our MES system. So the edge controller is the place where we do all the sort of processing. So this is where we do some embedded programming, and this is where we optimize the value stream. And this is the place without which none of the other things can be made possible. Right. So we have a very big responsibility in our hands. So the whole idea is, generally, when we work on edge computing, we will say that security should be done in application layer. So when we talk about the IP7 layers, right, we say that it should be done somewhere top the pyramid. But we have to ensure security is done from the very start. So almost now the power is, now the theme is this. Industry, they wanted to do everything at the edge itself. You'd even make prediction and forecasting at the edge itself. This is what they are telling. whatever the AI and ML thing which we do, whatever the algorithms which we develop in cloud, now we are trying to do that directly in microcontroller level itself. So that's the important thing which I wanted to say before we move on. And of course, there are other protocols like for the semiconductor industries like SEX and GEM. So generic equipment model. This is a famous model. So they use this to communicate and get device data when we produce. And again, we use different serialization like RS-232 protocol to somehow connect it to internet network. So you use RJ45 jack and you use serial communications to have interdata capabilities. So this is how we set up the edge processing. This sort of edge processing is how we will connect a factory device which is producing an item and connect it and derive value from it. So the first step is done. So of the 5 stages, edge processing is being carried out now. So this is the term, this is the model which I wanted to talk now. So whatever we do in edge processing, right, it will be done in this particular layer itself, in asset or in integration layer itself directly. This is the digitalization layer. The asset, imagine the asset as a robot. So that robot needs to be connected to internet so that it sends data to internet. But now in edge processing, we don't have to send data to internet. So whatever the capabilities which we wanted to do, we try to do all the 7 layers functionalities in edge device itself. So you use your asset, you use to integrate it with an help of an edge controller, and you use a communication protocol like OPCUA, OPCUDA, or maybe even MQTT, and then you channelize that and you send that information to your cloud solutions, or maybe you avoid that and you directly go to business layer and you make business decisions. For example, if the device is not functioning well, you have to pull the plug and you have to finish it off. So this is how you identify and you sort of move all the processing to edge itself. So this is the 3-dimensional view. We call it as RAMI model for Industry 4.0, reference architectural model. This is the standard things which people will talk whenever they wanted to digitalize a factory or whenever they wanted to build an IoT or industrial IoT solution. This is the reference model which they use. This is where they position their solution and say, hey, so our particular product, it will be lying in this layers, between these 2 layers, to make analogies. So digitalization of industry. So in this particular slide, I have to just highlight, right, so the different enabling components for our industrial IoT. So if you see the asset layer, right, like I mentioned, robot will go into the asset layer. You have the production equipment lying there, and also the different users who are interacting with that robot. That will be there in the asset layer. And then what was going to be the integration layer? You collect using sensors or maybe using human mission interfaces, HMI. You somehow connect that assets, right, and try to send information to internet or cloud, or maybe you process there directly. But somehow you want that integration layer. And then you use communication gateways like IoT gateway. That IoT gateway is nothing but OPCUA or MQTT, these protocols, or even an event broker. We will be talking about that event broker. The most of the slides which I have in future will deal with this event broker. And then we sort of publish information to different database. If you get time series data, mostly if we track a signal, it will be like a sinusoidal, cosine, or whatever signal sort of signals. It's good that we use time series database directly. Or if it's a video or audio data, you can process it like a batch. Or if it is something like a regular counter sort of thing, you can use stream processing. And then in functional and business layer, you make business decision. You assess the risk. Maybe you get some values. So all the AI and ML algorithm will be running in that functional layer. So this is where you say that, hey, if X and X happens, you have to produce Y. All those sort of decision learning rules will be automatically generated in functional layers using different algorithms. Finally, in business layer, you make decisions. You say that I'm using real-time monitoring and I'm using this visualizations, and I'm beginning to see that something wrong may happen and it's going north and I have to pull the plug. Or maybe if the production order has completed, let's say you are producing 500 units of shoes, you are trying to manufacture 500 units, and if 500 has been completed, you order a shipping cart to automatically come and pick it up. All the sort of decisions will be done in business layer. Okay, so now we moved to the first step. When we wanted to digitalize, we did all the edge processing. Now what happens, you begin to say and you begin to collect a lot of data, and you perform everything at the edge itself. But imagine, we will be collecting petabytes and exabytes of data. your edge controller or edge device is just a small thing. So maybe you use it to process all important data, but you can't just say that you wanted to store everything there. For computing, you can perform whatever you want in edge processing, but for storage, you have to move to cloud. So this is the most important thing which we have to understand when we begin to architect and when we begin to design this industrial 4.0 applications. Please remember, computing things and making prediction forecasting, that can be done quickly, but we as a factory, right, we wanted to have archives of record for compliance. We wanted to somehow say that, hey, in future if somebody comes and say, are you working in standards, is your particular production factory in line with so and so technologies, then we say this is our log for this particular month or this particular year, and we give them and say, take a look, we are following all the guidelines for this particular smart factory. So that's where storage and archival becomes a thing. So you have to somehow store it. So that's why we say you process every important decision making data at the edge, but for storage purpose, send it to cloud. So what is the idea of ingestion? So you have disparate data sources coming from multiple different systems. You use a broker or an informatics solutions, which we will discuss, and you ingest the data into a data lake. That is ingestion part. Okay, so I will discuss about how that ingestion part works briefly. What happens is, then once you inject and once you bring all the data into a single data lake, you will use a brokering services and ensure that data is distributed across multiple devices simultaneously. So what happens in data brokering stages? You begin to somehow use ETL solution. You load from machines, different devices, different papers, even some physical papers, and you convert it and you sort of use this data warehousing solution to build quick visualizations, alarming solutions, analytic solutions, and documents to and reports to give the users this is what has been collected so far and this is how we are processing it. So it's almost like a quick fix or a quick analytics thing which we do to leverage and use the power of analytics. So those sort of thing will be done in the third stage in brokering. That's the same thing which I discussed in the earlier stage. So data brokering, we are injecting everything. So the first part is data injection. We sort of use all the different disparate sources, we put it in a single lake, and then we process everything here in brokering, and we make visualization, custom dashboards, so siren or warning systems, report generation, and analytics. So all the things will be done here once we do that particular stage. So how we achieve? So I'm going to talk about a technology which is commonly used in industries here, that is Apache Kafka. So this particular Apache Kafka will take care of both the ingestion and brokering needs. So whenever we wanted to perform both injection and brokering, when we use this sort of broker, it will take care of all the needs and it will allow us to build insights across our value stream. So as a industry 4.0 engineer, we are responsible to we are responsible for our data. Without data, we have just an opinion. So somehow we have to build all the valuable insights. That is where we use this sort of broker. So this broker is very very easy. So it's normally like the it has a topic and a broker ID. So it will allow us to process data across multiple devices simultaneously. So generally, when we create a Kafka cluster, what we do is Kafka cluster is coming from Apache open source project. So Apache is this open software foundation which has been driving very big open source projects like Linux and things like that. It's equivalent to Linux foundation in some way. So what happens is when you create a cluster in Apache, you will basically give a topic ID so that equipment 1, robot 1 will send information directly to topic 1, and then robot 2 which is doing some other functionality will send to topic 2. Similarly, you will clusterize and you sort of distribute the workloads in such a way and track every devices in such a way that we manage to bring them together in a single centralized place, but we also distribute the workloads to different machines using these topic IDs and managing to do all the visualization, analytics, and reports. So basically, Kafka will have the concept of topics, and then we use this particular terminology to find out which device is being injected, and we find all the analytics related to that. Okay, so this is the insider information of Kafka. You bring in all the data together and then you put it in the data lake, and then you have the ability to do data replaying things and things like that. Okay, so Apache Kafka is a very good open source technology. For example, Uber, Netflix, LinkedIn, they all use Apache Kafka. use Apache Kafka to perform real-time interactions. So what we are doing basically here is we find out which are the technologies which has been successfully used in software field, and we are also bringing them to manufacturing and to our field. We are basically learning from each other here. So success of tech companies in how they process data, because they are very advanced in those areas. Those companies, they have been dealing with it since decades. We bring in their experience and their technologies, and we use the same thing for our factories, and we derive values. So this is the main important role for an industry 4.0 consultant. All right. So the next phase will be once you have the data brokering and once you do some sort of basic visualization. We call it like the exploratory data analysis. So if you are a data engineer or a data scientist, you frequently hear this terminology EDA. So in data brokering phase, you basically do exploratory data analysis. That's why you do this visualizations and all these things. The next thing is you have to somehow process a very big data. Remember the iceberg which I showed at the early. So it's a very big data, which is like around exabytes. So it's having like lot and lot of data. So you have to somehow process it, and you have to make sure you make a prediction quickly. So, so remember we saw that 65% of devices or 65% of data will lose value in just 2 seconds. If you don't act upon that data in manufacturing data within 2 to 3 seconds, it is of no longer use. It doesn't even have value. So you have to process it that much quickly. So you basically need large computing power, large resource to somehow make a prediction and quickly act upon it. That's how we reduce the gap between insights to action. Slowly we have to build a pipeline in such a way that data processing has been done in a quick and robust way to make the predictions. There are two sort of processing. So these are the, again, informatic terminologies, but I just briefly highlight them. In batch processing, we perform all the different jobs in a single run. So if you wanted to work with a lot of relational database or nothing but a different workloads, which is almost like the same set of jobs, which is going to be done. I will give you a real life examples. The payment processing systems, the debit card systems, whenever we use internet banking and when we do a payment, most of the things which is being done, that payment logic will be working as a batch. If you transfer from one account to other account, generally the transaction will get settled only at the end of the day. The At that end of the day, maybe in night 12 o'clock, they will run a huge batch job which updates the account and which settles all the things between different parties. So these sort of recurrent things, if we wanted to schedule something, we can use batch processing for factories. So stream processing is something which we need. If we wanted to act quickly, if we wanted to reduce the latency for making a predictions and things like that, you have to move for stream processing. You have to process it at that very instant, not at a particular point in time where you sort of gather a lot of data and process it as a single batch and update. So we will be moving more and more into stream processing in future. So this is where the industry is heading at. So remember, I was always talking about the insight to action time. I have beautifully highlighted it here in this particular curve. So see, if an event is happening, right? For example, let's say that we are using a robot which is lifting a device from place A to place B, and that robot is having a temperature sensor. And if the load of that particular thing which it is lifting is getting very heavier, the temperature will also increase correspondingly. So whenever I measured it with my sensor using my temperature sensor, if the temperature is high, I know that the robot is facing stress. So basically, it's exceeding its lifting capacity. The threshold is getting exceeded. So during that time, what I do is I have to immediately act and I have to immediately perform things to stop the robot from breaking. So, but this is what is happening right now. So if an event is happening, if I acted immediately, the value will be very high. But now what I'm doing, I'm collecting the data. And then I say that, okay, so now I see that the temperature is increasing. Now what I have to do? I do an analysis. And then I propose that we have to stop the device and send a warning. So all these things I'm doing slowly, and then I take countermeasure, and then it takes into account. So when the event is actually doing, and when we basically stop the robot, during that time, the robot may have even broken. So damage will be already done. So this particular curve should be reduced in some way that it should directly be in this stage, and we should somehow save the robot before the All these things are done. So that is why we say we have to move from batch processing to steam processing to reduce this curve. So you have to reduce the analysis latency, you have to reduce the decision latency, and you have to quickly act upon your data immediately to save the robot, to save the factory floor. You have to save the shop floor. So this is the whole idea behind all these things. This is the steam processing layer. So how we process using steam and how we make sure that this curve is getting reduced. That is the thing which we will discuss in the upcoming slides. So we wanted to do real time dashboard information. And initially what we do is we can't directly say we are going to build AI and ML because it's been used as a buzzword that people sometimes they misuse it in such cases. But generally we have to build a normal logic. First you build a decision tree and you decide how to act upon these things. Then you sort of train an AI ML model, maybe use reinforcement learning, because reinforcement learning is something which we directly use more and more right now in production. We automatically use RL for a robot to take decisions. So it will optimize for a reward, and based on that reward function, it will take a decision. So then you use predictive models. And then finally, you add more contextual data to data points received. So I have just told some technologies here for batch processing, which is used in batch processing, steam processing. So for example, in steam processing, we may use programming languages like Python, Java, R to quickly act and inject data and do some ETL loads. This is how Spark will be operated. So Spark is a library, so you can find Spark implementation in all major programming languages. You may have it even for Java, Python, Scala, R, all the things will be there. We will also discuss what will be the more important things which we wanted to do. So in order for us to reduce the curve, right, we have to process huge data. So that is why Kafka has been introduced. So Matej Zahera, he is one of the core developers of Kafka project. So he said that the main goal for me to conceptualize is I want a data scientist to program on huge data sets in an easy and intuitive way. You have to quickly act upon it. You should never feel that you are processing 10 TB data. So that is why it's taking 10 days to process. Somehow you have to clusterize it, and somehow you have to make sure that you use the available resources to the best possible way. Okay. So data enrichment is another important area which we have to do. So the important aspects is the data which we have. If we wanted to build an AI and ML model, we have to add more features. Feature engineering is a very important research area which computer science engineers will work on. If we wanted to build a better analytics and prediction models, it depends on the quality of your data. So data enrichments is something which we as engineers should take care of. Suppose the machine is not sending extra information, machine will just set temperature information, but we can add extra data like temperature at this date. So temperature at after 1 hour since production started, we can add more intelligent features on top of it. We can say that what is the ideal time of the machine, so, at what time the machine didn't work, and what was the active time of the machine. All the extra information can be act like an data enrichment or a data augmenter so that we make better decisions in future. So this is the data enrichment architecture. So remember, we collect all the devices information and process it at the edge. And then we use Kafka to process, use topic ID, we publish the information, we build all the information into the data lake. And then we use the stream processing engine where we process the event in a quick and easy, efficient way. And then we once again send it back using the feedback, and the new event is written what you have to act on. That thing will be written in the fourth part back to the data event lake. So this is the architecture which we follow in our factory. Okay. So different processing environments will be there. So once again, you have canonical data, and then you will have data from databases, RDBMS system, normal CSV file, employees register, their attendance register. So all the data should be pushed to your data lake, and everything should be processed using stream processing and then written back to Kafka in a different topic. So this is the data enrichment architecture. So I will just quickly go through this. So if we use a different industries, right? So these are all the common analytics architecture which has been used across different industries: supply chain industries, commerce, marketing, healthcare. You may have some different set of compliance. That is why we have these set of services available and bundled together. Dynamics 365 is an application. It basically uses Kafka in the backend. So if you are a finance company, you can easily choose this finance, and it will already have the compliance regulatory things pre-established for you. So you can easily work on your models and implement and produce good predictions and forecasting based on that. All right. So now moving further, we have how we use and aggregate the data from the different MES models. So now I talked about how we use real-time transformation. Now we also say what will be the idea for batch processing. So we talked a lot about stream processing, but there is necessity for batch processing as well. Like I mentioned, payment solutions. For payment solutions, if you do stream processing, it is not very ideal. It is resource intensive. So that is why you make a settlement every night, once per day. Similarly, when we build uh, a value stream pipeline or an industry 4.0 pipeline, we will ensure that some task like retraining the model should happen only once a day. I will explain why we retrain our machine learning model. Because factory is a dynamic situation. Every day we may get new insights. The longer we run and the longer the data we gather, our machine learning model which we built earlier may no longer be applicable for models of futures. So it is a necessity for us to build a model which will dynamically train on every day's data. So what we generally do is we follow this rule. We follow that for every single day. We have to collect the production log from our MES system, use different feature engineering features, and update our prediction models every single day. So maybe I will give you an example. The corona crisis started during end of March, right? So it started in Germany maybe a little earlier. But what we did was we begin to see different patterns because not every worker was there. The demand started reducing. So all the previous forecasting which we did were no longer applicable for us. So we decided to retrain. So we built a new machine learning model with the recent data and we redeploy. But if somehow we already had this particular pipeline where we say that run a batch job every day and update the model on a regular basis, then there will never be a reason for us to rework and rebuild the model. So this is the recent thing which I wanted to highlight. So quickly going on. So machine learning, why we use, obviously this is a very big area, but to say generally we use algorithms. We write a logic and we say, hey, if this is the input, you give the data, and if it follows this condition, this has to be the output. But in machine learning, what you do, you should no longer write the algorithm. The machine should find the algorithm. You just give the input and you just say this is the output for that input. Automatically, you use a machine learning model, any sort of model like basic regression models, classification models, SVM, neural net. At the end of the day, what it is decoding is it's giving you an algorithm which determines the relationships. So that is how you think statistically. What sort of things we use for industry? We use deduction, we use classification. We say, okay, so these are all the different products which are produced. So this is where we detect the breakdown, and the probability of this device failing down is lying between these two disks. And then we optimize it further. So if you add one more robot in this production line, you can save 20% of time. All the sort of optimization, all the hypothesis testing can be done in this phase. All right. So there are the four different layers of analytics. You basically say in descriptive what has happened. This can be done in the ETL phase itself. You transfer the data into information, and then you diagnose why did it happen, and then you will give using machine learning model. You make some predictive thing what will happen now, and then you say prescriptive action, what action to take. So all these are some things which data scientists will use as a mantra to deploy AI and ML application. But we will go one step further. We will use this prescriptive what action to take, and we will also act on it. So this is the job of industry 4.0 engineers and embedded engineers. So we complete the loop and we use these functionalities and even add more value on top of it, right? So we use different types of sensors to gather information for predictive maintenance. So you use bearing sensors, speed sensors, dynamic pressure for displacement, even if it is moving in a slight way, how to find that. And then of course thermistors or temperature, and then electrical power sensors to sort of get information for condition monitoring. And then for descriptive, you say that if the more noise is coming or if there are more vibration, you say that it may lead to the failure of the device. And using that, you give basic correlations and find out that if temperature is rising and then the device is breaking down, you do use some diagnostic models. And then you begin to predict the probability of failure or remaining useful time. And then you say after 5 hours of running the equipment completely, there is a wear and tear down happening on this device. So this sort of things can be done and predicted successfully using predictive maintenance thing. And ideally, this is the cherry on the top, you give even more deterministic model, and you say, since it's going to happen in 5 hours, run till 4 hours 45 minutes, and then give a 15 minutes break. This will allow you to save or prevent the breakdown from happening. That's prescriptive. So benefits of ML. So these are all some research work which has been done, and how we get the ROI. So I won't spend a lot much time, but like you can see here, the value realized is very, very higher. So companies are very much bullish. So what's in it for Germany? So this has been taken from McKinsey report. So what is the smartening up of AI is going to do for the industrial sector and industry 4.1 general. Right now, many projects are still in R&D phase, but once realized, the value is going to be very, very immense. So generally, we use ML to make quick visualizations and show that this particular data which we used is of good value. We identify different correlations. So this is just an example. And then we also say if it's not linearly correlated, but still it's somewhere correlated, we find out relationships in such a way that unknown circumstances may result in a correlation. So we have to somehow build a model which identify even spurious correlations. And then we also do significant testing and build a neural network. In our supply chain, we build a sort of a neural network to estimate the forecasting time for shipment. We give all the data, just like in the slide I showed earlier, right? We just give the input and output, and then we build a different neural network architecture in such a way that it produces and optimizes the result. So now we are at the end of the presentation. So what we generally do is we found out and we learned that how we use edge processing, how that is the most important phase without which none of this is possible. And then we went to different architectures of how to broker and how to build a data lake, which technologies we use, and what are all the ML and AI approach which we use to go from descriptive to predictive technologies. And now the final part is serving and output. So what will be the output? You build an alarm system, you build a dashboard, you build a visualization, and you say a breakdown is going to happen. So this is the output. So yeah, this is the final layer. I think it's a self-explanatory layer. So now putting all the things together, whatever I showed in different slides, this is the final full picture. Edge processing will be done from the device. You will also send that information. You will ingest it using the real-time database, and then use Kafka, and then you build everything. You enrich the data. You make some transformation. If then or this, then that, or then you build predictive models. You may use some different ML and AI algorithms. Once you do all the predicted modeling, you will serve it to output. So these are all the 5 stages, 5 different stages. We have just sort of beautifully summarized it in a way to say how these final 5 stages will look in big picture. Okay, so finally, I wanted to conclude with the business impact. So very, very interesting thing is, right, still we are in the nascent stage here. This arena is blossoming in such a way that in future we may realize its full potential. So as an active researcher, or as an active student who wanted to find out research possibilities, I would say this area is going to flourish in such a way. It's a very good research area to work on, very interesting area to work at, and the value will be realized only after 5 years. So this is a wonderful report from PricewaterhouseCoopers company. So predictive maintenance solution, right now organizations are only using 28%, but in 5 years it may increase to 66%. So take up all these areas and try to leverage and learn a lot and things, so that we can realize its full impact at its full capacity in near future. So connected factory, integrated planning, and then finding a digital twin and doing simulations. So you do confirm and checking, all these areas will usher in future. All right. So with that said, I will end it on this note. So I could either watch it happen or be a part of it. This is a famous thing which drives me every day. So I would say that we should all be a part of this motion. So thank you everybody for your attention. So we can take some questions. I would hand it over to.
So I thank our speaker for the nice and wonderful presentation. Now let us move on to question and answer session. I kindly request our speaker to clarify the doubts posted by the participants.
Yeah, absolutely, Manjula.
So the first question is difference. What is the difference between IoT and yes? So what is the difference between IoT and IIoT?
Yeah, absolutely. That's a good question. So in industrial IoT, right? So the concept of IoT is still going to be same. We are connecting things to the internet. So that is Internet of Things. So similarly, here we are going to connect industrial equipments to internet. Industrial equipments are little different. The dynamics is going to be changed. The vocabulary which we use is going to change. So normal physical things, the way we connect, it's going to be different when you connect a PLC to the internet. Ideally, the technologies and the communication layers will same, but the interface may look different. You may connect using RS-232 in a normal device, but in your IIoT, you may use some industry specific protocols there. So that is the difference. But the communication technologies and the way you communicate, it's most of the similar thing for both IoT and IIoT. I hope that answers the question.
So the next question is how to bring the academia closer to industry, especially in India. What do you think?
Very, very good question. So I would answer this question in two parts. I think right now the academia is getting in the right direction. So they are now working closely in tandem with what industry is doing. They are adopting those set of practices. But the best way to get into the motion is actually doing it. I would suggest that people should attend more international conferences. Academia should sort of attend both academic conferences as well as industry conferences. So IEEE has a different body for industries as well as a different body for academics. It's if both of these worlds meet together and if people across the industries exchange data, I think that would act as a bridge and bring both the worlds together. There shouldn't be a different places. I think that they act in silos. Somehow they should act in tandem with each other, held common conferences where experts from academics comes and presents their paper, and even experts from industries comes and shares their knowledge. This way both of them can act and they can exchange ideas, and this will serve as a very good bridge. And the second part of the question, how to improve it in specific to India, I think we should adopt more industries. So we should help industries to flourish. In Germany, one thing which I see here, right? In Germany, there are not just very big industries. There are not just very big tech giants like Siemens and Rexroth and Bosch. There are also normal family owned manufacturing industries. I think this should somehow be leveraged in India, because when we have MSMEs who are actually working in a lot of production and lot of optimizations, then we can slowly begin to improve and implement the solutions directly there, so that it no longer remain in theory, it can actually be worked in practice. Now only few manufacturing companies have set up shop here. Even if you take the example of mobiles, right? Basically people are telling that now the mobiles are being produced, but no, mobiles are getting assembled in India. It's not getting produced in India. We have to somehow bring that back. We have to optimize it in a way that we have more manufacturing units set up, so we can implement all the concepts which we discuss about IIoT and go and implement it directly there. So this is my answer for that particular question. Thank you for the question.
And the next question is do you
Manjula ma'am, your voice got broken.
think edge computing is going to revolutionize the world?
Okay, so I heard that question halfway, but I believe the question is, do you think that edge computing is going to revolutionize? Yes, absolutely. I'm very much bullish on that. So that's why I spent a lot of time emphasizing on edge devices and how it's going to change. See, now what is happening is people, and especially computer science engineers, they are working more and more directly on the edge. They are adding security components in edge devices itself. So ideally, my guess is 70% of predictive maintenance things will be done directly in edge. Only 30% of things where storage is needed for auditory and compliance purpose, those data will be sent to cloud. So people are directly going to edge. So especially in factories and manufacturing, I believe edge will be the way to go. Yeah.
And the last question is in IoT, how can we handle the large amount of data which we get from Industry 4.0?
Yeah, absolutely. So this is the major point of discussion for today. We discussed about how we will use Apache Kafka and brokering systems. So we directly use stream processing to handle. So I would leave it in this way. So please go back and refer the slides which we used here. Especially when you use stream processing, right? You will be able to perform and act immediately. So the way you reduce the time, you would have seen in the presentation how we wanted to reduce the time taken from we collect the data to the time taken to act on the data. So we have to reduce this curve from insights to actions. So this can be done by using stream processing. So we use the stream processing services like Apache Kafka to, to sort of act and to sort of bring the power and to process these big data in different workloads. So there are a lot of technologies. So Kafka is not the only thing. There are Databricks. So Databricks is an offering from Microsoft. We can use that as well. And then we have Hadoop. So Hadoop is a project. So Hadoop is nothing but you use a different terminology called HDFS, and then they process all the big data. So big data processing is going to be a very, very important topic. So I would also encourage us as embedded engineers or us as communication engineers to get accommodated with these arenas so that when we move to industry, we can easily work with them. Yeah, thank you for the question.
So we have now come to the end of the session. And at this moment, it is my great privilege to deliver vote of thanks on behalf of Meenakshi Sundarajan Engineering College. At the outset, I would like to thank our correspondent, Dr. K.S. Lakshmi, our secretary, Dr. K.S. Babai, our principal, Dr. K. Suresh, our Dean Academics, Dr. K. Umarani, for their continuous motivation and guidance to conduct this webinar in a successful manner. I'd like to thank our speaker, Mr. Hari Santhosh, for sparing his valuable time and sharing his knowledge with us.